My name is Guillaume Caron. I am associate professor at the University of Picardie Jules Verne in France and a researcher at the Joint Robotics Laboratory in Japan. Today I'm going to present the humanoid loco-manipulations using combined fast dense 3D tracking and SLAM with wide-angle depth images. First of all, the motivation of this work lies in the industrial context, where it is still done today some hard tasks by human operators, such as moving large and heavy objects from a storage place to an industrial machine across the factory. And accuracy is important because this big object, as you can see here on the picture, should be inserted in the industrial machine, a mock-up of it here in our laboratory. So the object is more than 100 kilo and is showing a diameter of more than 100 centimeters. So it's a challenge to manipulate it with the humanoid robot that is chosen here because, of course, the similar shape as the human operator in today's factory. And then the goal is, after moving this big object in the factory, insert in the industrial machine that is more or less the same width as the object. So that's why the accuracy is important. There are, of course, many challenges to achieve these tasks on the two parts of object local manipulation and material manipulation. So our group made several contributions to these issues, and today I'm focusing on the fast and accurate object tracking and the robot localization issues. First of all, we chose a quite recent sensor, the Azure Kinect camera, that is offering a wide-angle depth camera of 120 degrees field of view. This camera is set in the head of our humanoid robot, and the data captured by this camera is used for both the 3D model-based tracking using the dense depth map captured and its interplay with the SLAM, so localization and mapping, using both color and depth information. The 3D model-based tracking is done in order to align the 3D model of the object to manipulate and the depth map that is captured by the camera. So this is done by solving an optimization problem that minimizes the error between the two types of data. And it is done in a multi-scale approach, and at each iteration, there are three stages. So first, the 3D model is projected in the same plane as the depth map in order to do the point association, so dense point association. And from these correspondences, we can compute the rotation and the translation between the 3D model and the camera. And that convergence, the alignment between the 3D model and the depth map captured is ideal. So it works well for the object I mentioned, so the bobbin, but we also applied it to other objects like a wheelbarrow at the center, and not only to move the camera around the object, but inside also, as we can see on the right, where we move the camera inside the mock-up of a part of an aircraft. Once the tracking is succeeding, the goal is to know where the object under manipulation is in the factory, or at least with respect to the industrial machine that can be distant. So the 3D model of this industrial machine is previously aligned to a dense map that is computed before the manipulation, and this alignment is done by iterative closest point. It allows to transform the sequence of waypoints, allowing to insert the object in the machine within the dense map. And then we can run the localization while the robot is manipulating the object toward inserting it in the machine. But if we don't do online mapping, even if we have the previously built map, we may observe quite instability when the camera is in between two poses of the pose graph of the map. If we apply roughly the online mapping, so instability is not observed, but actually we will have big errors due to the fact that the object which is manipulated is added to the map. So the idea is to leverage the result of the tracker in order to remove the bobbin part or the manipulated object part from the data that will be used for the SLAM, for the localization and mapping. And when we do this, we prevent the both actually the instabilities of the estimation and the error. And we could apply this on our humanoid robot, HRP5P, that you can see here. To the right, top right, we can see the onboard views captured by the color camera in the head of the robot. The middle right, it's a top view of the 3D map in which the 3D model of the robot and the manipulated bobbin are shown as well. And bottom right is the depth map captured by the Azure Kinect camera, but shown as a point cloud with the false colors, the red being the farthest from the camera. And the 3D model of the bobbin is aligned to this point cloud. And you can see that to the left, the robot is at the end after moving along several meters of trajectory, inserting accurately the bobbin inside the mockup of the industrial machine. So we applied the same technique from different initial poses, slightly different environments, and also other objects and other robots. And moving from one robot to another and an object to another was made easy thanks to our framework, MCRTC. Thank you very much for attention, and feel free to visit our website and our YouTube channel.